Hi everyone! Today we're going to study first derivative tests. Let us first define increasing function. If the derivative of a function is positive over an interval I, then the function is increasing over I. Here we have an example of a graph over the interval from A to B. This is the graph. On the graph, we can see two examples of tangent lines. This is the first tangent line, and this is the second tangent line. Both tangent lines are leaning to the right. It gives us idea that the slopes of the tangent lines are positive. Here is another example of a function over the interval from A to B. This is the graph. On the graph, we can see two examples of tangent lines. This is the first tangent line. This is the second tangent line. We can see that both tangent lines are leaning to the right. It gives us idea that the slopes of these tangent lines are positive. Now let us read the graphs from left to right. We can observe that the graphs are going upward. In this case, we can say that both functions are increasing over the interval from A to B. Also, the derivative of the function over the specified intervals are greater than 0, or we say positive. Let us define decreasing function. If the derivative of the function is negative over an interval I, then the function is decreasing over I. We have one example here of a graph over the interval from A to B. This is the graph. We can see here also two examples of tangent lines. This is the first tangent line, and this is the second tangent line. Both are dotted. We can observe that the tangent lines are leaning to the left. It gives us idea that the slopes of these tangent lines are negative. Here is another example of a function over the interval from A to B. This is the graph. On the graph, we can see two examples of tangent lines. This is the first tangent line. This is the second tangent line. We can observe that the tangent lines are leaning to the left. It gives us idea that the slopes of these tangent lines are negative. Now let us read the graphs from left to right. We can observe that the graphs are going downward. In this case, we say that both functions are decreasing over the interval from A to B. And we say also that the derivative of the function at this interval is less than 0. And that means the values are negative. To illustrate, let us see this function described by the graph. We say that this function f has 4 critical points, the A, B, C, and D respectively. Now, the function f has local maxima at point A and point D. At point A, we say that the f prime of A is undefined. In here, the tangent line is vertical. At point D, the f prime of D is equal to 0. We say also that there is a local minimum at the point B. Here is the point, and we say that f prime of B is equal to 0. Now, the function f does not have a local extremum at the point C, although f prime of C equals 0. This is not a local extremum for the reason that the sign of derivative changes at all local extrema. Let us examine the sign of derivative to these 4 critical points. Look at point A. This is the graph over A. On the left side of A, the graph is increasing. So we say that f prime is greater than 0 or positive. On the right side of A, the graph now decreases. And we say that the derivative is less than 0. So at point A, the left side is positive while the right side is negative. Now let us consider point B. On the left side of B, the graph is decreasing, while the right side of B, the graph is increasing or going up. So it means to say, on the left side of B, the graph is negative, while the right side of B, the derivative is positive. Let us consider the point C. On the left side of point C, the graph is increasing, and we say that the derivative is positive. While the right side of C, the graph is again increasing, and we know that the derivative is positive in here. So at point C, the sign of the derivatives remains the same. Look at point D. On the left side of D, the graph is increasing, so the derivative is positive. While the right side of D, the graph is decreasing or going down, so the derivative is less than 0 or negative. Let us study now the first derivative tests. Suppose that f is a continuous function over an interval I containing a critical point C. If f is differentiable over I, except possibly at point C, then f of C satisfies one of the following descriptions. Number 1, if the derivative changes sign from positive when x is less than C to negative when x is greater than C, then f of C is a local maximum of f. Number 2, if the derivative changes sign from negative when x is less than C to positive when x is greater than C, then f of C is a local minimum of f. Number 3, if the derivative has the same sign for x is less than C and x is greater than C, then f of C is neither a local maximum nor a local minimum of f. In this video, we're going to find local extrema using first derivative tests. Here are the steps to find local extrema using first derivative tests. Consider a function f that is continuous over an interval I. Step 1. Find all critical points of the function f. Step 2. Divide the interval I into smaller intervals, using the critical points as endpoints. Step 3. Find f prime, or the derivative of the function. Step 4. Choose an arbitrary test point x in each of the sub-intervals of step 2, and evaluate f prime on those test points. If f prime is continuous over a given sub-interval, which is typically the case, then the sign of f prime in that sub-interval does not change, and therefore can be determined by choosing an arbitrary test point x in that sub-interval. The respective sign of f prime on a particular test point represents the sign of derivative in that particular sub-interval. Step 5. Use first derivative tests to determine whether the function f has a local maximum, a local minimum, or neither at each of the critical points. Let's see this example. Use the first derivative test to find the location of all local extrema for the function f of x equals x cubed minus 3x squared minus 9x minus 1. For our solution, let us do step 1, and that is to find all critical points of the function f. The first step is to find the derivative. So f prime of x is equal to 3x squared minus 6x minus 9. And from here, let us set f prime of x into 0. So we will change the left side into 0. So we have now 0 equals all the members of the right side. Then let us solve for x. Observe that the right side has a common factor, and that is the number 3. If we factor out that number 3, we will have 3 times the quantity x squared minus 2x minus 3. Let us simplify further by dividing this equation by 3. So the equation now becomes 0 equals x squared minus 2x minus 3. Then let us solve for x. We can solve this equation by factoring. So the factors are x minus 3 times x plus 1. And from here, let us equate each factor into 0. So the x minus 3 equals 0, and the x plus 1 equals 0. Solving for x in the first equation here, we transpose the negative 3 to the right. So x is equal to positive 3. And on the other equation, x plus 1 equals 0, the x value here now becomes negative 1. We can see here that we have two critical points when x is equal to 3 and x is equal to negative 1. Let us copy these critical points under step 1, just like we have here. Step 2 is to divide the interval I into smaller intervals, using the critical points as endpoints. We are able to find the critical points. Now, let us plot them in the number line. Here is our number line. We write here -1, and on the right is the +3. We can see that our number line here is divided into 3 sub-intervals. The first interval is here, and we name this as from -infinity to -1. Next interval is from -1 to +3. And the other interval here is from +3 up to +infinity. Step 3 is to find the derivative. A while ago, we were able to find the derivative from step 1. So that is f prime of x equals 3x squared minus 6x minus 9. Step 4, choose an arbitrary test point x in each of the sub-intervals of step 2 and evaluate f prime on those test points. We have 3 sub-intervals here. Let us choose arbitrary test point on each of the sub-interval. On the interval here, we can choose a -2, which is the first integer on the left side of -1. On the interval from -1 to +3, we know that 0 is part of this interval, so we can choose the number 0. On the third interval, we can choose the number 4. That is the first integer after number 3. Now, let us evaluate the f prime or the derivative on those test points. Let's start with this -2. So we have f prime of -2 is equal to 3 times the square of -2 minus 6 times -2 minus 9. The square of -2 is +4. 4 by 3 is equal to 12. -6 times -2 is +12. Then we copy the -9. When we simplify these numbers, the final answer is +15. We are more concerned on the sign of the number 15. So this positive represents the sign of the derivative on this interval. So we take a note here that we have a positive or the plus sign, and we know that we have an increasing function on this interval. Next is the f prime of 0. This is equal to 3 times 0 squared minus 6 times 0 minus 9. We can simplify this into -9. We are more concerned here about the sign of the 9. So this is negative. The negative sign represents the sign of the derivative in the whole sub-interval here. Let us take a note that we have a minus or negative sign, and we have a decreasing function over this sub-interval. Now let us evaluate f prime of 4. This is equal to 3 times 4 squared minus 6 times 4 minus 9. The square of 4 is 16. 16 times 3 is 48. -6 times 4 is -24, then minus 9. When we simplify this, the final answer is +15. Again, we are more concerned on the sign of this number 15, and that represents the sign of the derivative on this sub-interval. Let us take a note here of plus sign, and we know that there is an increasing function over this interval. Now, step 5. Use first derivative test to determine whether the function f has a local maximum, a local minimum, or neither at each of the critical points. Our first critical point is -1. The left side of the -1, the derivative is positive and it is increasing, while the right side of this -1 is negative, that is decreasing. So we say that at x equals -1, the sign changes from positive to negative. Thus, there is a local maximum at x equals -1. Next, the other critical point is 3. Observing the sign of the derivative on the left and right of this critical point 3, we say that at x equals 3, the sign of the derivative changes from negative to positive. So we say that there is local minimum at x equals 3. Using GeoGebra, this is the graph of our function here. We can see on the graph that there is a local maximum at x equals -1. This is the point. Also, there is a local minimum at x equals 3. This is the point. This is now our final answer. Today we're going to study concavity and points of inflection. Let us define first concavity. Let f be a function that is differentiable over an open interval I. If f prime, or we say if the derivative is increasing over the interval I, we say the function f is concave up over the interval I. If f prime is decreasing over the interval I, we say f is concave down over the interval I. I have here one graph over the interval from A to B. On the graph, there are examples of two tangent lines given in dotted lines. This is the first tangent line. This is the second tangent line. Looking at the graph from left to right, we can observe that the slopes of the tangent lines are increasing. Thereby, we say that the derivative is increasing over the interval from A to B. In that case, the function f is concave up. Another example is this graph over the interval from A to B. On the graph, we have two tangent lines again. This is the first tangent line. Here is the second tangent line. Looking at the graph from left to right, we can observe that the slopes of the tangent lines are increasing. In that case, we say also that the derivative is increasing over the interval from A to B. In that case, the function f is concave up. Third example is this graph over the interval from A to B. In here, we have two tangent lines. This is the first. Here is the second. Looking at the graph from left to right, the slopes of the tangent lines are decreasing. In that case, we say that the derivative is decreasing over the interval from A to B. We know that if f prime is decreasing over the interval, we say that the function is concave down over the interval from A to B. This is our fourth graph over the interval from A to B. On the graph, we have two tangent lines. This is the first tangent line. This is the second tangent line. Looking at the graph from left to right, we can observe that the slopes of the tangent lines are decreasing. So we say that the derivative is decreasing over the interval from A to B. In that case, if f prime is decreasing over the interval, we say also that f is concave down. There is a note. If the derivative is constant, then the graph of f is said to have no concavity. Let us now define point of inflection. If the function f is continuous at the point A and f changes concavity at the point A, the point A, f of A is an inflection point of the function f. Here I have a graph, and on this graph we have 6 tangent lines. This is the first, second, third, fourth, fifth, and sixth. When x is equal to A, we have this point of the graph. Let us observe that the part of the graph on the left side of A, we're going to look at the graph from left to right, and we can see that the slope is increasing. Meanwhile, the part of the graph on the right side of A, please observe that the slope here is decreasing. Now this point with coordinates A, f of A is what we call the inflection point, because this is the point where the function changes concavity. A while ago, we say that on this interval here, the slope is increasing or the derivative is increasing. So this is a picture of the function which is concave up on this interval. While the right side of A, we notice that the slope or the derivative is decreasing. So on this interval, that the function is concave down. There is a note. Inflection point occurs when the second derivative of x is equal to 0, or if the second derivative of x is undefined. Let us go now to the test for concavity. Let f be a function that is twice differentiable over an interval I. If f double prime of x is greater than 0, or we say that if the second derivative of the function is positive for all x, an element of the interval I, then the function f is concave up over the interval I. Second, if f double prime of x is less than 0, or we say that if the second derivative of the function is negative for all x, an element of the interval I, then the function f is concave down over the interval I. Today, we're going to find points of inflection and intervals of concavity. Here are the steps to find points of inflection and intervals of concavity. Step 1. Find the second derivative of the function x. Step 2. Find the inflection points. Inflection point occurs when f double prime of x equals 0 or f double prime of x is undefined. For the first case, when f double prime of x equals 0, we can do this by setting the f double prime of x equals 0 and solve for x. The resulting value of x is the inflection point. Letter B. When the second derivative is rational, or we say a fraction, set the denominator to 0 and solve for x. The resulting value of x is the inflection point, and that is the point when the second derivative is undefined. Step 3. Divide the interval into subintervals using inflection points as endpoints. Step 4. Choose an arbitrary test point on each subintervals and evaluate the second derivative of the function on those test points. Step 5. Test for concavity. We say that if the second derivative of the function is greater than 0, or we say positive, then the function is concave up over that subinterval. If the second derivative of the function is negative, or we say less than 0, then the function is concave down over that subinterval. Let us see this example. For the function f of x equals x cubed minus 6x squared plus 9x plus 30, determine all intervals where f is concave up or concave down. List all inflection points for the function f. For our solution, let us do step 1, that is to find the second derivative of the function. The function is here, so the first derivative will be f prime of x equals 3x squared minus 12x plus 9. Therefore, the second derivative will be 6x minus 12. Let us copy our second derivative below step 1. Step 2 is to find the inflection points. We say that inflection point occurs when f double prime of x equals 0 or f double prime of x is undefined. Observing our second derivative here, this is a polynomial function. So it means this is defined in all its domain. Thus, it falls on the first case only. So we set the f double prime of x equals 0 and solve for x. So we have now 0 equals 6x minus 12. Let us now solve for x. This negative 12 we will transpose to the left side. It becomes positive 12 equals 6x. Let us divide this equation by the coefficient of x, which is 6. So we have here 12 over 6 is equal to 2. So the value of x equals 2. This is our inflection point. And we say that inflection point occurs when x is equal to 2. Step 3. Divide the interval into sub-intervals using inflection points as endpoints. Initially, the interval is all real numbers. So first, let us write our x-axis, and we put the number 2, being the inflection point, in the middle. In this problem, there is only one inflection point. Now, let us identify the corresponding sub-intervals. On the left side of 2, the sub-interval is from negative infinity to positive 2. While on the right side of this number 2, the sub-interval is from 2 to positive infinity. Now, we have the step 4, and that is to choose an arbitrary test point on each sub-intervals and evaluate the second derivative of the function on those test points. On this interval, we may choose the number 0 for easy computation, while on the other interval, we may choose the first integer after 2, and that is the number 3. Now, let us evaluate the second derivative on those test points for the 0 and the number 3. The second derivative is here. Let's begin with f double prime of 0. This is equal to 6 times 0 minus 12. And the answer here is simplified into negative 12. Next is f double prime of 3. And this is equal to 6 times 3 minus 12. 6 times 3 is 18, minus 12 is positive 6. Now step 5. Let us test for concavity. We say that if the second derivative is positive, then the function is concave up over that sub-interval. Also, if the second derivative is less than 0, or say negative, then f is concave down over that sub-interval. So look at our f double prime of 0, the answer is negative 12. Because this is negative, we say that on this sub-interval, the function is concave down. While the second derivative with respect to number 3, the answer is positive 6. Because this is positive, we can conclude that on this sub-interval, the function is concave up. From step 2 a while ago, we found out that the inflection point occurs when x is equal to 2. So the point is 2, f of 2. We want to get the actual value of this f of 2. So let us evaluate the function with respect to 2. So we have f of 2 equals 2 cubed minus 6 times 2 square plus 9 times 2 plus 30. We can simplify 2 cubed into 8 minus the 6 times 2 square is 24 plus 9 times 2 is 18 and then plus 30. When we simplify the numbers here, the answer is 32. So the coordinates of our inflection point is 2, 32. Let us take a note of this inflection point in here. Now using our graphing facility, this is the graph of our function. We can see that the point 2, 32 is the inflection point. Look now on the sub-interval on the left side of 2. You can see that the function here is concave down, while the sub-interval on the right side of 2, we can see that the graph is concave up. This is our final answer. Today we're going to study the second derivative test. Suppose f prime of x equals 0 and f double prime, or the second derivative, is continuous over an interval containing the point C. If the second derivative is greater than 0, or we say positive, then the function f has a local minimum at the point C. If the second derivative is less than 0, or we say negative, then the function f has a local maximum at the point C. If the second derivative of x is equal to 0, then the test is inconclusive. Let us see this example. Use the second derivative to find the location of all local extrema for the function f of x equals x raised to 5 minus 5x cubed. For our solution, the step 1 is to find critical points when f prime of x equals 0. This is our function here, so the first derivative will be 5x raised to 4 minus 15x squared. Let us set the first derivative into 0. So the left-hand side will be 0 equals 5x raised to 4 minus 15x squared. Now let us solve for x. Let us factor out the greatest common factor to each of the terms. So we have 0 equals the 5x squared times the quantity x squared minus 3. Now, let us equate each factor to 0. So we have the 5x squared equals 0, and this x squared minus 3 equals 0. Solving for x in the first equation, we have x equals 0. On the second equation, we can transpose this negative 3 to the right, and then let us take the square root of both sides, and the value of x is equal to plus or minus the square root of 3. We have now these critical points, and we say that the critical points are the values when x equals 0, square root of 3, and negative square root of 3. Step 2. Find the second derivative of the function and evaluate it using critical points of step 1. A while ago, we solved for the first derivative. Now, the second derivative is equal to 20x cubed minus 30x. We can simplify this expression into 10x times the quantity 2x squared minus 3. Now let us evaluate each of the critical points into the second derivative. Let's begin with the f double prime of 0. This is now equal to 10 times 0 times the quantity 2 times 0 square minus 3. The 0 here outside makes the whole equation into 0. So the f double prime of 0 is equal to 0. Next, let us evaluate the f double prime of the square root of 3. This is equal to, we can simplify the radical and the power 2. So the number 3 here comes out as positive 3 to be multiplied to 2. So we have 6 minus 3. The difference will be 3, and that 3 will be multiplied to 10. So the f double prime of square root of 3 is equal to 30 square root of 3. Next, let us evaluate the f double prime of this negative square root of 3. This is now equal to 10 times negative square root of 3 times the quantity 2 times the square of negative square root of 3, then minus 3. We can simplify the expression here by cancelling the radical and the power 2. But take note, the negative sign here becomes positive. So when we cancel it out, the number 3 here comes out as positive 3 to be multiplied to the number 2. So we have 6 minus 3. And the difference is 3, and that 3 is to be multiplied with a 10. And everything now is simplified into negative 30 square root of 3. For step 3, let us now use the second derivative test. We say that if the second derivative is greater than 0 or positive, then the function f has a local minimum at the point C. Second, if the second derivative is less than 0 or negative, then f has a local maximum at the point C. But if the second derivative of the function equals 0, then the test is inconclusive, meaning there is no conclusion. Let us see now this f double prime of 0, and this is equal to 0. In this case, we say that it is inconclusive when x is equal to 0. Next is the second derivative of square root of 3, and the answer is positive 30 square root of 3. Since this is positive, we say that there is local minimum when x is equal to square root of 3. For the third critical point, and we have here the f double prime of negative square root of 3, and we found out that the answer is negative 30 square root of 3. Since this is negative, we say that there is local maximum when x equals negative square root of 3. Using the graphing facility, this is the graph of our f of x is equal to x power 5 minus 5x power 3. Let us examine the graph on its critical points when x equals negative square root of 3, when x is equal to 0, and when x is equal to square root of 3. We say that there is local maximum when x is equal to negative square root of 3, and it's here. Also, there is local minimum when x is equal to square root of 3. This is the point. And then, there is no local extremum when x is equal to 0. This is the point. This is now our final answer. I hope you learned something from this video. See you again next time.